Hi, and welcome to the second of three lectures on the foundations of vectors. Um, the last lecture, we took a look at what it meant to be a vector and looked at how you would break one up into pieces to make it useful for something like physics. We also looked at the method of parallelograms as a way of interpreting how to add vectors together, at least graphically. What I would like to do today is to talk more about adding vectors, specifically how to add two different vectors together. Now, we're not going to do it graphically per se. We're going to develop a method for adding them together by component. So, let's put two vectors here. We'll go with the black one to begin with. Actually, let me be consistent from last time and use a smaller one right here. This, and we'll go purple. Here's another one right here. There we go. Two different vectors. Let's give them names. Again, I'm not very creative. This is vector A, and this is going to be vector B. Now, if you remember, when we used the method of parallelograms to add things together, what we did was to create complementary vectors, make a parallelogram, and then cut the parallelogram in half. So let's put our third one there, presuming this is going to cooperate. Oh, look at that. That's going to be vector, we'll say, A plus B, or C. Okay, so what I want to do is to build up, like I said, a method for adding these things together without having to use the method of parallelograms, basically. And to do that, what I want you to do is to recall what we talked about last time when we first showed that you can break a vector up into pieces. You have pieces that lie explicitly along the x direction, and you have pieces that lie explicitly along the y direction. So what I'm going to do is to draw those here for each one of these vectors. So we'll start with A first. Oh, did it again. I'll get used to it. Now let's do B. It's hilarious. And then we'll do C. That. Get to make the whooshing noises. Always draw from top down on paper. Takes a little getting used to. Now, so here's what we have. This piece right here along the x-axis up to this point would be AX. And this piece right here would be AY. Looking at B here, this piece right here would be BX. And this piece right here would be BY. Now, when you add A to B, you get this third vector C. This long thing right here would be C's y part. this plus this would be C's x part. Now let's take a look at what that means. So look, the y part, cy, is what you get when you take and you add ay's length to by. Ax plus bx is cx. So what that means is that when you add a and b together to get c, what you're really doing is adding the components of a and b together. Now, watch what happens when I multiply these things through. Ax, x hat, plus bx, x hat, plus ay, y hat, plus by, y hat. Now I'm going to group them by letters. And this right here is the component form of A. This right here is the component form of B. So as you can see, when you add two vectors together, what you do is you break them up into components, and then you simply add the components together, and it's internally consistent. And that's how vector addition works whenever you're looking at components, which, like I said, is the preferred method of doing it in physics. So let's work an example. So once again, we have two vectors, A and B. There's A. Oop. Well, Y decided not to attach to the head there. That's B. And what I'd like to do is to find not only the components, but also the magnitude and the direction of C. So this is vector A, this is vector B, and this is what you get when you add them together. So in order to add these things properly, we're going to have to add them by component form. Now here, let's call A (40 meters per second). The angle that A makes with respect to the x-axis, 45 degrees. B has a length of 25 meters per second, and the angle it makes with respect to the x-axis, 5 degrees. Now, what I'd like to do is to find C in component form, that is Cx and Cy, but also magnitude and direction form. So that would be something like something meters per second with an angle of something with respect to the x-axis. Now, just by looking at the angles here, I can tell you that whatever we get is going to lie in, obviously, this quadrant right here. So there's not going to be any weird coordinates that we have to deal with, or what's the word I'm looking for? Yeah, I guess coordinates works. So there's nothing weird we're going to have to be dealing with here. All right. So anyway, let's break some stuff up into pieces first, which is how we have to start with this. If you look here, A is 40 meters per second, makes an angle of 45 degrees with respect to the x-axis. B, 25 meters per second. Whoop. An angle of 5 degrees with respect to the x-axis. Now, if you look here, and let's just, we're going to play the same sort of game that we did before. Just to make our lives easy so you can see how this works. That. Something right here. I'm gonna have the special effects here. Like that. Okay. Now let's just this right here is AX. This is AY. This is BY, BX. This is going to be CY, and then this big thing right here is going to be CX. All right. So here, if you write out your trig rules for A, we'll start there. We have sine of theta sub A and cosine of theta sub A. Now, sine of theta sub A is going to be related to opposite over hypotenuse. So that's going to be AY over A. Cosine is going to be AX over A. And these two right here are going to give us this. Now, conveniently enough, since this is 45 degrees, the answers for the x and the y parts are the same. For A, 28.28 meters per second and 28.28 meters per second there. So that's the A part. Now the B part we'll do right here. So again, actually I'll do the angle part stuff here, and then we'll actually do the calculation over here. Sine of theta sub B, if you look at B, the sine part is going to be this part, again it's y. Cosine of theta sub B is this part right here, is the x part. And if you solve for by and bx, 25 meters per second sine of 5 degrees, and this is cosine of theta sub b, 25 meters per second cosine of 5 degrees. So when you actually carry these calculations out, for bx, you get 24.9 meters per second. And for by, you get 2.18. Now these numbers might seem a little funny, but if you actually take a look at the vector b right here, you see how so much of its length lies along the x direction and very little lies along the y direction. So by merit of that, you would expect a y part that's much smaller than the x part, and that's what we see here. Now, remember, when you add these things together, all you do is you add the components together. So if I want to find, for example, cx, that's going to be ax plus bx. What was ax? Well, that's up over here, 28.28 meters per second. What's bx? Well, we just found that here, 24.9 meters per second. And when you add those two together, you're going to get 53.18. Now the y part, you just add the y parts together. 28.28 meters per second plus by 2.18. And when you add those two together, you're going to end up with 30.46. So here, the vector c, written in component form, would be 53.18 meters per second in the x direction plus 30.46 meters per second in the y direction. That would be your vector. Now, in terms of magnitudes and directions, we need to actually use the Pythagorean theorem and our trig rules for that. So here, if you think of c as just being this one long vector that has a y part and has an x part, you can write out its trig rules. And the only one that's really relevant to us here is going to be tangent. So tangent here of theta sub c, and theta sub c would be this angle right here. Okay. Tangent of theta sub c is going to be opposite over adjacent, or cy over cx. So again, theta sub c is the inverse tangent of the y part over the x part. It just happens to work out that way now. The y part was 30.46. The x part, 53.18. And when you actually do that, you're going to get 29.8 degrees. Now, what's the length of c? Well, that's the sum of the squares, square root of. (53.18 meters per second squared plus 30.46 meters per second squared. You take your square root and you end up with let's see, actually do the calculation here. .46 divided by 53.18. Actually, what am I saying? That's not what I want. The square root of 53.18 squared plus 61.29 meters per second. So, what's C equal to? Well, in component form, don't forget your units. So that's the component form right there. And then magnitudes and directions would be 61.29 meters per second with an angle of 29.8 degrees. Right there. A lot of work, I know, but unfortunately it's very important. Now, so that's simple addition. Now, subtraction works exactly how you would think. Instead of adding the components, you subtract the components. If you have a vector that points off in a different quadrant, like for example this one over here that might have a negative x component, when you add them in, like if you're doing addition, you would add the negative in, which means that that part would actually be subtracted. So things work exactly as you expect, with the added complication that unlike regular nice whole numbers where you just add the numbers together, here you actually have to break things up into components. Now, the next thing I'd like to discuss is multiplication. We've done division, or not division, but we've done addition rather. In subtraction is just what happens when you add a negative. So what I want to do now, like I said, is multiplication. Now, multiplication is it's unfortunately the most complicated one. So let's see here. There we go. Do a little bit of a blank page here. So far, whenever you add two vectors together, or you subtract, you do components. That's what you do. Pretty easy. That's all everywhere. Multiplication is more complicated. There are three types of multiplication that you see used in vectors. You have what's called scalar multiplication, you have what's called the dot product, and then you have something that's called the cross product. It's also sometimes called the vector product. Vector product. Now, in terms of easiness, this is the simplest one, this is the next simplest one, and this is the most complicated one. What type of multiplication do you need to use? Well, the situation that you're dealing with will tell you that. But before we get to that, let's try to develop a sort of a geometrical understanding, a visual understanding of what's going on with these. So the first one I want to start off with is simple scalar multiplication. So we know a scalar is just a number, and numbers can be positive or negative. So let's pretend that you have a vector, once again we'll call it A. And what I want to do is I'm going to multiply it by 2. So we're going to take A and multiply it by 2. So, if I were to visualize that vector this way, This is A. Two A would look like this. Twice as long. Okay? It's twice as long. So the way to interpret multiplying things by a scalar is that it causes the vector to either get longer or to get shorter depending upon how big the scalar is. For example, if this right here was A and this is 2A, this would be about 1/2 A. Now, that's positive numbers. A negative number flips the direction 180 degrees. So, a positive scalar scales the length of the vector. It doesn't change the direction. Okay? Now, a negative flips at 180 degrees and scales it. So, for example, if this right here were the vector A, this right here would be minus A. So, let's play a game. Let's think of vectors as distances and directions that you walk. Let's pretend that you walked from the tip or from the tail of A all the way to its tip, and then you walked from the tail of minus A all the way down to its tip. You see how you haven't really gone anywhere? Well, check this out. A plus minus A gives you 0. The 0 vector. And if you think back to our last lecture when I talked about an algebra, the 0 vector is an example of a 0. Now, what's the 0 vector mean? Well, that's a little more abstract. That means that all of the components, the x parts, the y parts, potentially even the z part, have a value of 0. It's not the same thing as just being 0 by itself. The components have a value of 0. Now, here, just as an example, if you took and you wrote minus 1/2 A, just so we're clear, that would be the same thing as A flipped 180 degrees and cut in half. That's scalar multiplication. So, let's talk about the dot product. Okay, so the next thing I want to talk about is the dot product. Now, unlike the scalar product, which gives you a vector back, all it does, remember, is to change the length of the vector or potentially switch the direction as well by 180 degrees. The dot product gives you a scalar back. It gives you a number. Now, interpreting it graphically can be a little funny, but one way you can envision it would be like this. So I want you to think about two vectors. So we'll say here's one vector. I'm going to call this one B. And then here's another vector. I'll call C. So vector B and vector C. Now this is the angle that sits between B and C. So the dot product actually has a definition. It's written typically as B dot C, and that's the same thing in this particular case as C dot B. And two ways to write it would be the following. Bx times Cx plus By times Cy plus, if there were a z part, Bz times Cz, you get the point. Or you can write it the following way. It is the length of B times the length of C times cosine of the angle in between. Now, it's this one right here that I want to take a look at to kind of get an idea of how you can think of the dot product. And to help us do that, what I want to do is to draw a fake set of coordinates. So, we'll use dotted lines because they're fake. I'm going to use color green, I think. Actually, let's use red. So here's our fake coordinates right here. This would be the y direction. Always makes me laugh. This would be the y direction. This would be the x direction. What I want to point out here is that B lies entirely along the x direction. So that said, those parts right there are the x and the y parts of C. And thinking about our coordinate systems and all the stuff that we've done so far, cosine is adjacent over hypotenuse, or Cx is C cosine of theta. The length of C, cosine of theta. So a rough way of thinking about how to interpret the dot product is that it gives you the part of a vector that lies in the direction of another vector. Now, mathematically, it's pretty easy to do. For example, let's pretend that you had vectors that look like this. We'll say we've got 2. C, 20 meters. It makes an angle of 30 degrees with respect to the x-axis. D, 35 meters. It makes an angle of, oh, I don't know, 50 degrees with respect to the x-axis. So let's draw our vectors here. This right here would be, this is C vector, and this is D vector. This angle right here, theta sub C, 30 degrees. This angle right here, theta sub D, 50 degrees. And the angle between them, 50 minus 30, or 20 degrees. So the length of D is 35 meters. The length of C is 20 meters. C dot D, which would be the same thing as D dot C, would be 20 meters times 35 meters times cosine of 20 degrees. And if you do the math on that, times 35 times cosine of 20 658 about meters squared. Now, we use dot products a lot of times in physics to look at things like work, which you may have seen in calculus if you've had Calc 2 and done some integration. We also use dot products to talk about how much of something passes through an area. We'll be talking about that mostly in the second semester of physics. Now, let's do another example of a dot product, but this time let's look at it from a component standpoint. So, let's pretend that you have two vectors. We'll use C and D again. Is 2 meters per second in the x direction plus 3 meters per second in the y direction is C. D, 5 meters per second in the x direction plus 1 meter per second in the y direction. So, how would you draw these things? We'll do C again in black. It is 2 up to 3, if I can get it to go there. There's about C. D, five and up 1. It's about there. So, this is C, this is D, and unlike our previous ordeal with dealing with vector addition, here it's not necessary that we take and we express these things in magnitudes and directions and do angles and all that stuff. As I pointed out over here, an equivalent form of the dot product is this right here, adding them by multiplying the components together. All right. So here, two times 5 is 10. 3 times 1 is 3. 10 plus 3 is 13 meters squared per second squared, whatever that is. So this is a fully equivalent way of doing the dot product, doing it by looking at the components. Now, in the next video, we're going to discuss the last way that you multiply vectors, and that's through the cross product. And the reason why I want to dedicate an entire video to it is because it's mathematically more complicated and it's difficult to visualize.